And there's no simple answer, because as you've just learned, if you have only a few, then this means for the landmark assignment, it is good. Because if there's only a few, it's hard to confuse them. On the other hand, it means for the localization that if there are only a few landmarks, we will have less observations, so our accuracy is low. Or even if there is too few, we will have parts in our trajectory where there are no observations at all, and so as we only run the prediction, our position error will grow quickly. So and conversely, if you have many landmarks, then our localization is good. However, it's easy to confuse them. Now, in order to have many landmarks for a good localization and still not to confuse them, we need distinct landmarks. So remember that in our case, all landmarks were the same, because in the real world, they actually have exactly the same dimensions. But in practice, they may be different in dimension or, for example, in color. So if we had used a camera in addition, we would have been able to detect the different colors of our landmarks. And then we could have added the color as a component in the description of our landmark. And now this does not need to be a color, it can be anything. So it can be the dimensions of the object. It can be a detector that detects if a surface is flat, or it detects the curvature of a surface, or if there is a dihedral edge, or even if there's a corner. Likewise, it may also be that our camera detects an image of the object, and we are able to detect feature points for which we can derive a high-dimensional vector of descriptor values. And so in general, the idea is to use landmark signatures so that our landmark is described by its position and also its signature. And so if our robot sees a new landmark, and the question is if this should be assigned to an existing landmark, it does not only use X and Y, but also the signatures to decide this. Now, when do we actually assign landmarks? Now, our algorithm worked in the following way. A robot scanned and detected a cylinder, and then we looked within a certain radius for the closest landmark, and if we found one, we assigned it, and if not, we generated a new one. Now, this assignment used a fixed radius, and in our case, we experimented with a radius of 50 centimeters and also 40 centimeters, and we found out that the algorithm is brittle with respect to this parameter. Now let's think about this fixed R. Does it actually make sense? Imagine the following. A robot is here, it measures this cylinder and that cylinder. Now here, there is a landmark in our map, which we have observed very often, and consequently, the error ellipse for this landmark is pretty small. On the other hand, say there is also a landmark which is a bit further away from this measured cylinder than this distance. On the other hand, the uncertainty of this landmark is really large. So obviously, in this case, I should not assign the landmark to this measurement, whereas in this case, I should assign it. And in detail, upon deciding this, I should also take the uncertainty of the robot into account. And it is pretty easy to do so. And it's called maximum likelihood landmark assignment, and it uses the following. So C is our measurement, and our function h, our measurement function, takes the state and predicts a measurement. So the difference of this is the difference between the real measurement and the predicted measurement. And this is a measure how well the landmark fits to our measurement values. Now don't use this directly because that wouldn't take into account those variances. Rather, I form this product with the inverse of a matrix psi and C minus h without the transpose, where psi is a covariance matrix which I obtain using the following formula. It is h, the Jacobian of our measurement function, times our predicted covariance of the state times ht plus q. And it's easy to see why this makes sense, because q is the measurement error captured in this covariance matrix. This is our error in the state, so if I multiply from the left by h and from the right by ht, I just propagate this error through the function h. So this is error or variance propagation. And so what comes out is the error in measurement that is due to my error in the robot's position and orientation. And so I add those up. So basically, this part is due to my error in the state, whereas this part is my error which results from my measurement. So I bring those two together and I compute this value and then use a threshold when to accept the measurement based on this error. So this should be smaller than a threshold. This is also called the Mahalanobis distance, and you have seen that earlier because in the normal distribution You remember the probability density function was something like a constant times e raised to the power of minus 1/2, and here we had our x minus mu transposed times the inverse of our covariance times x minus mu. And so thresholding this value essentially means setting a threshold in a Gaussian distribution and accepting all values which are in this range. So this is called the maximum likelihood landmark assignment. There's one more thing I want to mention regarding landmark assignment. This is the provisional landmark list, and this works as follows. Say our robot is here, and now it sees a landmark for the first time, but now we will not put this landmark into our state vector as a standard landmark. Rather, we will say it's in a provisional landmark list. But still we will give the landmark its associated covariance matrix. Now if the robot moves on and it observes the landmark again, then our covariance matrix will decrease. But we will take the landmark into our final landmark list only after several measurements indicate that we have found the landmark consistently. So in this case, we will put it into our final landmark list in the state vector. Now how can we handle that in practice? And this is actually relatively easy, because the idea is the landmark is still put into the state vector, but the equation is modified so that for this landmark in the provisional list, the observation equation that is set up only handles the position of the landmark as an unknown, but not the robot's position and orientation. And so in this case, the robot will influence by subsequent measurements the accuracy of the landmark, but the landmark won't influence the robot's position as long as it is in the provisional list. So it is handled just in the same way as a final landmark, only we keep a flag, and due to this flag we use a slightly different observation equation. So this brings me to the conclusions. What we have learned this time is SLAM, the technique that gave the lecture its name. And we learned there's a full SLAM problem where we compute the posterior over all states and assignments of landmarks. And we learned this is usually computationally infeasible. So we learned about the online SLAM, which is easier to handle, and this uses a deterministic computation of landmark assignments. So instead of providing the full posterior over all states and assignments, we assign on the fly using a deterministic algorithm. And this is also its main drawback, because as we saw, it's brittle with respect to landmark confusion. Also, even though the online SLAM is less complex than the full SLAM, it still has a huge update complexity that grows with the number of landmarks, because the size of the state vector grows with the number of landmarks, so it is potentially unbound. Nevertheless, online SLAM has been used by many groups with considerable success. And as you have seen, for a small problem, it has worked out perfectly. So congratulations! This time, you have learned about the online SLAM, and you have implemented the extended Kalman filter version of the online SLAM, which for the first time solved the problem of localizing our robot without having a map in advance. So now for the first time, we can just put our robot somewhere and it will build up a map and localize itself in the map it has just built. So congratulations again, you made the step from localization to mapping. We will elaborate on this topic further next time, and I hope you join me for the next unit.